Cool. Good morning, everyone. My name is Zilu Wang,
And I'm Nehal Patil.
and today we're going to present our final project, exploiting broadband Wi-Fi. So platform security is an integral part of the security of complex systems. Researchers have been paying much attention towards application processors, but much less focus has been put on the rest parts. Today, we'll explore the exposed vulnerabilities introduced by Broadcom's Wi-Fi SoC on mobile devices, which will allow us to remotely gain code execution on the chip. In the past decade, the use of Wi-Fi has become commonplace on mobile devices. While vendors started to producing more complex hardware like full media access control Wi-Fi SoCs, the overall security of the device could be weakened. To start looking for the bugs, we're going to locate a set of functions which are used to parse and retrieve information from a received frame and work our way backwards from there. So Wi-Fi management frames encode most of their information in small tagged chunks of data, called information elements. These chunks are structured where the unique tag and length fields are 1 byte long. Broadcom used one function to extract IEs from a frame called BCM parse TLBs, which is also present in the firmware's ROM. So we can now cross-referencing locations which call this function and reverse each of these call sites. So there are two bugs that we found, both related to TDLS, are present on the devices that we are working on. So good news is triggering these TDLS vulnerabilities can be done without requiring any action on the part of device being hacked, and also without indication of hacking. To give a brief introduction towards tunnel direct link setup, also be shortened as TDLS. So it happens when two peers on the same Wi-Fi network wish to transfer large swath of data between one another. It sounds wasteful to pass the entire data stream from the device to the AP and then to the Chromecast. TDLS comes into play here to provide a means of peer-to-peer communication on a Wi-Fi network that is AP independent. There are three phases in connection through TDLS. The first is the discovery phase. When a Wi-Fi client sends out a TDLS discovery request frame to a peer, a TDLS capable peer that receives this frame responds by TDLS discovery response frame. The request and response are correlated to one another using a 1 byte dialog token. And second, to set up a connection, a three-way handshake needs to be done. This handshake not only indicates the success of establishing connection, but also derive a TDLS peer key, also short for TPK, to secure the traffic. And finally, the two peers can exchange traffic once connection is created. If one side wishes to end the connection, he will send a TDLS teardown frame. Upon reception of such a frame, the TDLS peer will remove the connection and free up all of the related resources. And now let's start to look into detail and figure out where are some possible overflow opportunities. A high-level logic of the setup function derived from reverse engineering is as follows. Although the function verifies that the RS and IE's length did not exceed the allocated buffer's length, it fails to verify that the subsequent IEs also do not overflow the buffer. And as such, setting the RS and IE's length to a large value will cause the timeout interval and fast transition IEs to overflow the buffer. And for example, assuming we set the length of the RS and IE to its maximum possible value, 224, we arrive at this placement of elements. Orange fields are irrelevant for the overflow since they're positioned within the buffer's bounds, and red fields indicate values that cannot be fully controlled by us, and green fields indicate values which are fully controllable. For example, the snaps value is chosen by the TDL's initiator during the first message in the handshake, so can be arbitrarily chosen under our control. And similarly, the code for teardown stage is as follows. The FTIE's length field is not verified to ensure that it doesn't exceed the length of the allocated buffer. This means that simply by providing a crafted FTIE, we can trigger the overflow. And as shown in the picture at the bottom, those spare data that is not subject to any verification and can therefore be freely chosen by us. That the overflow's extent is quite limited. We can only override at most 25 bytes beyond the range of the buffer. And now I'm going to give over to my teammate to dig more into how to write the exploit.
So yeah, I'm going to go over how the exploit was written. The end goal here is to insert some shellcode into a place in memory that can be controlled. There's a couple things that need to be looked at and set up before that can be accomplished. In order to achieve an overflow, we need to first create a TDLS teardown frame with an overly large FTIE. And that is done here with the green highlighted code. We cause 25 bytes of OXAB to be written in the overflow. This overflow will happen during the TDLS teardown phase, which happens after the connection setup. The next issue is how do we know whether the overflow has actually happened? To do that, we first look at how Broadcom implements their version of a heap. They use a best fit allocator with coalescing and a free chunk list. Chunks are allocated based on the smallest chunk that is large enough. This is what they look like. Notice the size and next pointer. They're important pieces of this exploit. This is what the free list looks like at the bottom after we send out the crafted TDLS teardown frame. We can see that one of the chunks has an exceptionally large size, and it's also important to note that the firmware does not crash during this. Now that we know we can make an overflow, we want to look at the heap during the setup and teardown methods. We want to hook the malloc and free functions, which basically means insert code that intercepts function calls. Once we do that, we can adjust the malloc and free functions to add traces that show us every operation occurring on the heap. We can then create a visualization of the heap, shown here, while creating a TDLS connection. The x-axis is space and the y-axis is time. Red means the chunk is in use, while gray means it's free. Looking at this at the top left, a conclusion can be made that besides the heap activity during the connection start, there's not much else going on. Everything else is done in place. This means that the heap structure is very consistent, but it also means that our control over the heap structure is limited. At the bottom, that's the heap structure during the teardown phase, which is much more open. The image in the top right is the state of the heap after setting up a TDLS connection, which is where we will be working in during the overflow. Two chunk holes exist, and if we use the hooks we attached before, we can see the allocation of a 256 byte buffer, which is what we overflow. We then make the conclusion that our best fitting chunk is probably in one of these holes, and we choose the one with size OX11C. Our overflow will then overwrite the header of the next chunk and a couple bytes of the content of that chunk. Included in the content of this chunk is the size field. If you corrupt this size field by making it a larger value, we could cause the next free operation to create a free chunk whose tail overlaps another heap chunk. Once a free chunk overlaps another heap chunk, any further allocations in which the overlapping chunk is a best fit would be taken from the end of the chunk, thereby corrupting whatever fields are at the tail. We want to create a heap state where two free chunks overlap one another. If we get that, allocations taken from one chunk can be used to corrupt the next pointer of the other chunk. By overriding the size field with the value 72, we get this heap state here at the bottom. So after tearing down the connection, we get a zero-sized free chunk overlapping a larger free chunk. To achieve this, we need to make what's called a controlled allocation primitive, which will ideally control both the size and contents of the allocation. We can use the data structure that handles the TDLS action frames and routes according to an action code. What we are interested in is the out-of-spec frame with code 127. Digging in further to this, we find this implementation at the bottom, which allows us to send a frame even after the connection is torn down. So here, A is our controlled allocation with a defined lifetime, size, and content. So to summarize again, we want to create two overlapping chunks and use our controlled allocation to allocate memory from the tail of the larger chunk and point the smaller free chunk to a location we choose, which will be an in-use chunk. If we make that chunk be the best fitting chunk in the free list, we can get our own data to be allocated in there, replacing the chunk's contents. The last thing we need to use are timers, which are periodic events that happen in the lifespan of a connection. We want to replace the contents of one of these timers with our own data and point the timer at the address of our shellcode. It's also fortunate that our heap is executable due to the memory protection unit, or MPU, setting all memory as RWX, which makes the protection's job pretty useless. So putting it all together, we can hijack a code chunk to store our shellcode, then hijack a timer to point at the shellcode so that once the timer expires, the shellcode will be executed. And that's the exploit. After Broadcom was notified of this issue, they updated their firmware to properly use the MPU and added additional hardware security. Thanks for listening to our presentation.